Okay, good evening. Welcome to
MathyMath number 121.
MathyMath number 121. We had to talk a little bit about something tonight, and because you have an early school day tomorrow. And I thought it'd be interesting to talk about a different four-dimensional shape. What's the four-dimensional shape that you think of first when you think of four-dimensional shapes?
Well, the hypercube.
Okay, and why is that a shape you think of?
Well, it's just a shape that I've seen a lot.
Okay. Yeah, and I think that's probably what most people think of when they think of four-dimensional shapes. But it turns out that there are actually analogies or similar shapes in four dimensions to all the Platonic solids. And there's even an extra one in four dimensions. And the shape that we're looking at here is called the 5-cell. And what do you think this is analogous to in this four-dimensional? This is a three-dimensional version of a four-dimensional shape. What do you think the three-dimensional analog is?
It's tetrahedron.
Tetrahedron, okay. Why do you think it's called the 5-cell?
Well, there's not really 5 areas. There's a lot of fours in here.
Oh, okay. Like what fours do you see?
Well, there's 4 yellow struts, 4 green struts, 4 triangles on the outside. These lines separate the tetrahedron into 4 areas.
Okay. But remember, we're looking at a three-dimensional projection of the four-dimensional shape. So these are all good things, but it doesn't quite look like this. It's a four-dimensional shape. Apparently our dog does not like four-dimensional shapes.
So how could this, well...
Why do you think it's called the 5-cell?
Well, maybe it's one of the more simpler kinds of cells. Like the 120 cell was really complicated.
That's true. The 120 cell was super complicated. Super complicated.
There's really not many 5s in here.
Do you see any 5s in there?
Well, I see 5 vertices.
Okay, that's interesting. 5 vertices. What do you think the two-dimensional analog of a tetrahedron is?
A triangle with... I think it would be a triangle with a dot in the center and like lines... An equilateral triangle with a dot in the center and lines going to it.
Okay, so what... that would be a two-dimensional projection?
Yeah.
But what do you think the two-dimensional analog?
Oh.
So not the projection. What do you think the two-dimensional analog?
A triangle, equilateral triangle.
Okay. So in 4 dimensions, this is called a 5-cell, and you saw 5 vertices. How many vertices did you see in 3 dimensions? In 2 dimensions?
In 2 dimensions, there's 3.
How many in 3 dimensions?
There'd be 4.
Why?
Because you don't have this.
Ah, okay. Cool. How many in 3 dimensions? How many faces were there? How many two-dimensional faces were there?
In 3 dimensions, there would be 4 faces.
Okay. In 2 dimensions, how many one-dimensional faces were there?
3.
Okay. So how many 3-dimensional faces do you think there will be?
Probably 5.
Okay. Now, what do the faces look like? So in 3 dimensions, what do the faces of the tetrahedron look like?
Wouldn't the faces of this 4-cell? 5-cell?
No, in 3 dimensions.
Oh, they look like triangles.
What, any special kind of triangles?
Equilateral triangles.
Okay.
So then in 4 dimensions, the faces should look like tetrahedrons.
Okay, so let's see if we can find 5 tetrahedrons in here.
Well, I see 4 pretty, well, yeah, 4 pretty easily.
Okay, where do you see 4?
There's one on this face going to here.
Okay, that could be a tetrahedron.
There's one here,
Uh-huh.
one here, and then one underneath.
Alright, so we're just missing 1 tetrahedron.
Well, would the big tetrahedron count?
Ah, interesting. Why do you think that would be a 1 as well?
Well, because it's sort of warped since we projected it. So maybe it's like more up and these are more spread out.
Okay. So, if we had a... could we calculate the sort of surface area here?
Well, wouldn't the surface area be the volume of the 5 tetrahedrons?
Very good. Very good. And if we could calculate the volume somehow of this in 4 dimensions.
Well, you'd have to do like length times width times height times something else.
Yeah. then that would give you the volume of a cube.
And then, but then you have to modify it because you have a different shape.
Yeah, that's true. That's true. What's the area for a triangle?
It's 1/2 base times height.
How about a pyramid?
Area of base times height over 3.
So what would you guess the volume formula is going to be for a 4-dimensional pyramid?
Probably volume of base times the height over 4.
Interesting. Okay. So we might be able to do an analogous calculation to what we did for Patrick Honnor's 3-dimensional shapes.
Mm-hmm.
And we could maybe find a value of pi for this tetrahedron, or this 5-cell, I mean. Do you think this looks much like a 4-dimensional sphere, or do you think it's very far away from being a sphere?
Pretty far away.
All right. Well, maybe we will attempt that calculation tomorrow.
All right.
All right. Good work, hon.